request anyone who Ma'am Melanie Jane Militia to lead the opening prayer. Thank you, Ma'am Melanie. So we will start immediately now. It's already 1:31. For the attendance, I have sent the link here in the chat box. I hope you have access the attendance link already. And I think there are some concerns regarding the attendance now. By some of you have not accessed the link previously, but all of the 3 attendance link are already sent yesterday in our group chat. So I hope na-access na siya sa tanan. And then I think there are some concerns on BISO. BISO nga email, email, university email. Ikaw lang, Ma'am Richelle, Ma'am Sinahon, ang wala pa naka-fix sa university email, or there are still others wala pa na okay ilang university email. So, regarding sa concerns on university email, pwede na to i-contact ang EDP, but I don't know if makontak ba na sila via chat, murag face to face jud na sila i-contact. However, if dili jud siya ma-okay, pwede raman nako just inform me. Pwede raman ako i-send or i-email nako ang activity, no. For topology class, I only have sent one activity, one lecture notes, pero always na ko siya i-update, and then one activity pa. Second activity will still be sent in the upcoming days. So katong dili ma-okay, please inform me using sa atong GC. Pwede ra jud ko inform using sa atong GC, ha. Yeah, kuan na lang, Ma'am Rachel. Try to access kay I have sent you the code. VPN na ko ang code, so i-access lang siya basin pwede ra, basta kay ang ako magong gigamit is university email. Unlike with the Google Meet, kung university email akong gigamit, and then ang inyong email na gigamit kay dili university email, personal email, pwede ra na ako ma-admit, but dili pa ko sure sa G-class kung okay ba ko maka-admit o dili university email. Try lang, ma'am, ha, niya inform me if unsay result.
Okay, ma'am. Thank you, ma'am.
Sige, so kanang we will resume now with the reporting of outputs. Last time we end up with 46 to kabuo. Alright. Am I right? Ang last reporters, last Sunday are si Sir Cortidor, si Sir Ampak, si Sir Barete. Dili si Sir Barete, si Sir Albert. Sir Albert, and then Ma'am Ampong, Ma'am Daog-Daog, Ma'am Pinia Flor. So kato lang no? Ang 6 kabok nga naka-report last time. Sakto ba ko? Mamilesyo also. So there are 1, 2, 3, 4, 5, 6, 7. And si Sir Hamor, ay, ito apelido ni. Si Ma'am Hamoran. So, ito, 1, 2, 3, 4, 5, 6, 7. So, may 7 ka-reporters last time. Okay, so pwede ta mag-start ni ready na ka, Sir Boletti, ikaw mag-start or lain nga person atong mag-start kon. Okay ra ka, Sir Alan?
Okay ra kog lain, ma'am.
Sige, sir. Sige po.
Kay gamay
Ako sa
gamay ra
check.
gud gamay ra gud kay nako ma'am kay wa mahuman. Murag ginubo ra gud kay nako ako'y pa-reporton pero sige pawahilan ako ma'am kay wa man makadimaon nako sa base sa nakit-an ako bitaw sa ilaha. Muna murag
Okay
maawa
naman,
ko
sir.
muna.
Pwede naman ka mag-start. Dili ka na muna. Sige, arita mo
Oo,
start.
wala ko ma'am. Pawahilan ko.
Bawas, ako
Sige.
i-check sa kinsay first. Sige, so.
Pwede ra po ko ako nilay muna ma'am ug kuan. Pwede ra sad
Sige,
ko.
sir. Ikaw na lang, sir.
Sige.
Para i-arrange na ko.
Sige ma'am.
Sabi ko dali. Sige, sir. Ikaw lang, sir, ha?
Okay. Maura ni ma'am ha sa ako aran ning pagsabot.
Sir, ato lang tan-awon, sir.
Okay. Okay,
I-correct.
mus So pwede ko maka-screen share ma'am.
Yes, sir. Start na, sir.
Okay, so dar. Continue. Dili man maklaro.
You are using laptop, sir, or cell phone?
Sa cellphone na magahorang gi-download siya. Nani siya? Dito mo pa lang ako. Kuan sa lang ko ma'am, kanang di mo pa nakuha ma'am. Nabalin ko sa laptop.
Sige, sir. Sige, sir.
Yeah.
Proceed sa kasalain, sir.
Sa lain ma'am, kaya di mo pa nakuha.
Next to Sir Barati is we have Ma'am Miranda. Ma'am Miranda, can you have Ma'am Miranda? How about Sir Kasimsiman? Any concern, sir? Or ikaw mo volunteer nga mo start?
Ako na lang volunteer, ma'am. Start ko, ma'am.
Sige, sir. Did you submitted a hard copy?
Yes, ma'am. Nakasubmit ako, ma'am, sa G-Class.
Sa G-Class, pero wala diri sa concern na. Ay, wala yung hard copy, sir, no?
Wala, ma'am. Kanang soft copy ra to, ma'am.
Sige, sir. Kuan lang, ina ka Saturday pohon mag-request ko og hard copy, ha? Sa submission.
So i-print to na, ma'am.
Yes, wala to ni mo gisuwat, sir.
Wala, ma'am. Ako ratong gi-encode.
O pwede na po i-print siya.
Okay, ma'am.
For a while, sir, ha, kaya akong i-access ang imong i-submit.
Okay, ma'am. Thank you, ma'am.
Kasimsiman. One. What are the pages? What are the pages? Okay, ready, sir. Sige, so na-access na ako. Sir, you can start.
Ma'am, i-report to tanan, ma'am, or magpili lang ko og item adto.
Kuan lang, sir. Kanang only one sub subcomponent sa theorem 1.10, sa theorem 1.21, and theorem 1.23, and then proceed to number 2. So topology and topological space, open sets and closed sets, and then going to larger topology. Also, I think there is still one katong illustration sa theorem 3.11. So,
Okay, sige, ma'am.
sige, sir. Pwede na tayo mag-start, sir.
Okay, ma'am. Ako sang i-share screen, ma'am.
Ah.
Nakita ra, ma'am.
Sir, pwede na tayo mag-start.
Nakita ra, ma'am.
O, makita na, sir.
Okay. Saan man eh. Kana, ma'am, nara, ma'am.
Yes, sir. Makita na, sir.
Okay. So, pandakan. Ayan. Okay, good afternoon, everyone. I am Paolo Angelo Simsiman, and this is my answer from the past activity. So we have illustrate theorem 1.10, theorem 1.21, and theorem 1.23. So we have here number 1. This states that any set is a subset of itself. For any set A, every element in A is also in A. Example is we have let A, we have 3 different fruits here. We have apple, banana, and cherry. So to show that A is a subset of A, so every element of A, for example, we have apple, banana, and cherry is in A, thus A is an element of A. Next, we have number 2. If A is an element of B and B is an element of A, then A is equals to B. This states that every element of A is in B and every element of B is in A. Then A and B contains the same elements. Like for example, we have A equals B. Let A be there red, green, and blue, and B is red, green, and blue. So to show that A is an element of B, every element of A is in B. So to show that B is an element of A, we also have every element of B is in A. So kung unsay naa ni A, naapod ni B, unsa po naa ni B, naapod ni A. So since A is in
is an element of B and B is an element of A, it shows that A, A is equals to B. Next number, we have number 3. If A is an element of B and B is an element of C, then A is an element of C. This states that if A is a subset of B and B is a subset of C, then A must also be a subset of C. This is a transitive property. So let A is equals to circle and square, B circle, square, and triangle, and C is we have circle, square, triangle, and hexagon to show that A is an element of B. Every element of A, for example, we have square and circle. We have B is equals to, B is an element of C. Every element of B nga naa ni C. And also the A is an element of C. Every element of A is napod ni C. So since A is an element of B and B is an element of C, it follows that A is an element of C. That is according to the transitive property of subset relations. Asa ay next ani ma'am kani ma'am?
Yes, sir. Only one, you choose only one from Theorem 1.21, sir. Either from idempotent laws, associative
Kani
laws, commutative, and taap to De Morgan. So, mamili lang kag isa, sir. I explain.
kini na lang idempotent loss. Okay. Union, we have A, union A is equals to A. We have intersection A intersection of A is equals to A. For example, we have let A equals to 1, 2, and 3. So we have A union A equals to 1, 2, and 3. Union 1, 2, and 3 equals 1, 2, and 3. So kung unsay na ani A,
Sir, di ka madunggan, sir.
wala.
Madungog ra man ari.
Madungog ra, madungog ra.
Madungog
na
yun,
to,
sad. Madungog ra pud ari.
Okay. Mapadayon lamang ko, ma'am. Kisa tayo
Sir,
nga
patay na, sir. Madungog na, sir. Si Sir Rafael ang dili ka dungog din.
Okay. Madungog ra nimo, ma'am, sa uban.
Yes, sir. And the rest.
Okay. Sarap ba to? Dara. So, we have intersection A, intersection A, we have 1, 2, and 3, we have 1, 2, 3. So, in both cases, we see that the set remains unchanged. So, in the idempotent laws, there will be no changes because kung unsay na ani A, because since they are all the same, so A union A intersection to A. Kung unsay na ani A, kay since A naman sila tanan, so walay mawala, walay mausog nila. That is according to the idempotent laws. Next ma'am, kani ma'am.
Yes, sir. Next theorem na, sir.
Kani.
Okay na to sa theorem.
Okay na to kani ma'am, okay na ni ma'am.
Number 2 na, sir. Number 2.
So, dara. Mao ba ni? Okay. Okay, provide example for the following components. Okay. We have A, define a set. Consider a set X is equals to A, B, and C. A topology on a set X is a collection of topology of subsets of X satisfying the following conditions. Ma'am, correct naman ko ma'am kay wala pa ko
Okay,
kayo
sir.
pa.
Nag-follow ko sa imong gi-submit, sir.
Sige ma'am. You have the empty set and X itself are in the topology. Ay, unsa ni pagbasa ni siya ma'am? Asa to?
Tao.
Tao.
Oo.
Tau. The union of any collection of sets in tau is also in tau. The intersection of any finite collection of sets in tau is also in tau. So let's have here example. Let's define a topology on X. One possible topology on X is tau is equals to empty set. We have A, you have AB, and we have ABC. So to verify the following conditions, condition 1, the empty set, and X. X ano siya, ma'am? X are in tau. we have the we have the empty set is an element of tau where x is equals to a, b, and c where it is an element of the tau. So both are satisfied. Condition 2, the union of collections of sets in tau is also in tau. We have A union AB is equals to AB element of tau. A union ABC is equals to ABC with the element of tau. AB union ABC is equals to ABC element of tau. The union of any combination of these sets, including the empty set, results in a set that is in tau. So that is according to the condition 2 where the union of any collection of sets in tau is also in tau. Kung unsay naa ni tau kung unsay naa sa sets, it is also in the tau. The condition number 3, the intersection of any finite collection of sets in tau is also in tau. A intersection AB is equals to A. So kuha na nato ilang intersection. We have here an element of tau. A intersection of ABC is equals to A. So A ang ilahang intersection. AB intersection ABC, we have the AB. So the intersection of any combination of the sets, including the empty sets, results in a set that is in tau. Since ang ilahang intersection is an element of tau, so therefore it is also present in tau. Since all three conditions are satisfied, tau is indeed a topology on X. So, moto siya ma'am, arita sa theorem number 3.11. Number 3 na ko ma'am.
Sir, sige, sir. Open set pa, sir. Sets and closed sets and neighborhood.
Dara. Open sets in this topology are kani ma'am is ako running your research ma'am. Dili ni ako own answer. The open sets in this topology. Yes, kapartam ni siya dito sa babaw. The open sets in this topology are the empty set 1, 1, 2, 1, 2, 3. Closed sets. The component of empty set is X, where X minus the empty set is equals to A, B, C. The complement of A is B, C. The complement of A, B is C. Paano pa ito eh? The complement of A, B, C is the empty set.
Answer ka ng sa imuhang open sets, you are using the set 1, 2, 3, sir, no?
Oh,
But
yes.
sa imong closed
Yes.
you are using
Let.
different set. So, ilet, kana na siya. Later, pwede na later na gagawin siya. So, mag-let
Hangal.
X, sir. Let X be the set
Kani.
ABC
ma'am.
ba?
Kani.
Lahi man siya.
This will be A, B, and
At
C.
okay raman na, sir, kay you're using 1, 2, 3 sa imong open sets. Dili ra sa closed set.
Ay, dari na lang siguro. Dari ma'am.
O, ng closed sets. Ubos
Kani
pa.
A.
Ubos pa, sir. Ay,
Close.
okay na, sir. Okay ra na.
Sa closet. Closet.
Ayan.
Kana.
So we have kani ma'am, himoning one no?
O, answer. Pwede lang dili, sir. Ayan na lang na i-correction ka ng just input what is your X kay para makahibaw tag unsa iyang complement.
Dari sa iba kani harabaton ma'am. Dari sa
Ulit.
ibabaw ma'am. Kaning set kani ma'am.
Wait. Dili, sir. Kanilang X nimo sa closets nga imong gigamit karing babaw katong kani diri sa topological space.
Oh, ma'am.
Sige.
Kani.
Sige, sir. So, ang imong X ani is the set ABC dai, sir, no? Sige, sir. Okay na, sir. Go on.
Arita sa neighborhood. Yes, neighborhood of X for all X is an element of X. A set N is a neighborhood of point x, element of x, if there is an open set U such that x is an element of U subset of n. For x is equals to A, we have AB, and ABC. For XB, we have AB and ABC. And for the neighborhood of X, for XC is equals to A, B, and C. So mo to sa kaning neighborhood of X. So arita sa larger topology. Apil pa ni ma'am, no? Yes.
For a while, sir. Wait. Ang imong topology, tay sa kuan day, sir. Sorry, sir. Pwede ka atong kuan na lang daan. Comment na lang nako daan.
Sige ma'am, sige ma'am.
Ang imong topology is, ang imong tao kay MTA, AB, and ABC. Wala ni mo siya gi-X.
Oh, wala
So,
GX.
Muni ang imong neighborhood
Yan.
nimo sa C,
Sa C is si
ABC, which is equal to X. I'm
Oh,
used to representing the whole set manggod by X. Okay ra, sir, sakto ra guys.
sige.
So katong the whole set na pwede na ka mo make use of X instead of enumerating.
Pwede ra day ma'am.
Pero wala lang
Pwede.
guys, sir. Kuan lang because sayop topo. Sakto ra day ang collection. Sige, sir.
So pwede ra dito siya og extra tong isuwaton din na nato enumerate ang kuan. Okay. A larger example, let X is equals to A, B, and C. We can define a larger topology X as follows. We have the empty set A, B, AB, BC, and ABC. Now let's verify that it satisfies the conditions of a topology. Contains, number one, we have contains the empty set, and X. Closed under arbitrary unions, consider any collection of sets. So we have here an example. Arita sa last part, the union of all subsets in T is equals to union and to set union to A, union to B, union to AB, union to BC, union to ABC is equals to ABC, where it is an element of tau. Okay. Closed under finite intersection. Arita sa last part, we have here the intersection of all subsets in tau is an empty set, union to A, union to B, union to AB, BC, and ABC. So mo to ang iyahang intersection sa ato ang topology. Okay. Last, arita sa theorem 3.11. The definition of topology, a collection of subsets of X such that the empty set and X are in T. The union of any collection of sets in T is also in T, and the intersection of any finite collections of sets in T is also in T. So we have here an example to illustrate that the intersection of topology is a topology. Okay, we have T1, and let's set X, let X is equals to A, B, and C. T1, we have empty set X, we have A and AB. Arata sa 2, we have empty set X, B, and BC. The intersection of these topologies is we have the empty set NC X. Muna ilahang intersection. Check the properties of a topology with empty set and X are in T1 intersection of T2. So we have here kani sila. Since A since A is naa sa T1 but wala sa T2, sa AB pod wala naa sa T1 but naa sa T2. So ang giingon diri is ilaha ramang intersection. So we have here empty set og si X. To illustrate that the union of topologies need not to be a topology. So ganina atong giingon is topology is a topology. Si karon na pod is union pero topology not be a topology. For example, we have X is equals to ABC. We have T1. T1 includes empty set X, A, and AB. We have the union of this T2 is empty set and X where B and BC. The union of these topologies is we have ang union nila is kung unsay naa ni T1 or naa nilang duha. We have empty set X, we have A, B, B, and BC. So we are going to check the properties of a topology since empty set and X are in T1 union T2. So they are considered as the union of the set. Consider the sets A and BC. Their union is ABC is equals to X is in T1 union T2. So si A is umayon taog union kung unsay naa nila katibukan. So silang unsay naa diha mo i-include sa ato ang union. So in particular ato sa last we can see that A union B is equals to AB is in T1 and T2 dara. But another example could break the rule. So mano to siya ma'am. Last na part.
So, thank you. Thank you, Sir Paulo. So, congratulations na. Anya, kuan lang, some few comments for further enhancement. Akong i-share ang screen.
Okay, ma'am.
Okay, so, nakita akong screen? Yes, ma'am. Nakita na akong
Ma'am,
screen. Ay,
makita
yes,
ra ma'am.
sige. Nagulan sa inyo, ha? Ito, kanilang sa idempotent laws, sir, no? We are to show nga ang A union A is equal to A. So, okay man atong justification ang kanilang we will add this one. Kaya kung mag-show ta o equality, ipakita nato we are trying to manipulate one expression and then in the final part sa ato ang justification makita nato nga equal jud siya sa A. So sakto ni siya we get the union of A and A 1 2 3 union 1 2 3 and then that is equivalent to 1 2 3 and if we notice ang si 1 2 3 is equal to A. So kana lang siya sa inyong solution and then
Katong naka-red na mo to yung kulang.
katong naka-red. Pero okay na gud siya kanang for on how to express it as
justification ra siguro mo.
complete justification or
Okay. Thank you.
o ingani siya ingani ta mag-arrange og arguments and then next is okay na to karing diri sa answer kanang sa topology, no? How are we going to show that a certain collection tau from a power set of X is a topology? Okay ni siya nga naatay gi-exhaust nga union. Kay first condition empty and tau, okay naman na siya, no? Clearly, makita na to siya sa topology ang empty and X by mere inspection. Sa condition 2, kuan siya, ihurot na to og exhaust ang union. So, A union AB, A union ABC. Pasakto man siya, no? AB union ABC. ang kulang na lang kay agi statement po nato diri sir nga the union of any combination of these sets including the empty sets results ato na lang X. So include the discussion, include the computation or the discussion that the union of X to all other members of the set results to X, no? Which is in tau.
Okay,
Para
ma'am. Thank you.
ma-satisfy niya ang condition number 2. And so with the intersection, so i-include po na to ang intersection sa X. Kay
Okay.
first is ang empty intersection all other members of tau, and then second is ang X intersection all other members of tau, and the rest na kaninang gi-show na to. Ana lang gud siya.
Okay, ma'am. Thank you, ma'am.
Kanya katong nag-shift ta og example ni atong gilet sa babaw kay 1 2 3, so motong butang na to ang specific nga X, no, kay the complement or the open sets are respective to the elements of X man. So kana ako lang gibutang diha. And then kani kaya same suggestion earlier, exhaust all the arbitrary unions of the members of tau here. Or if not, kung dili magani nato i-display ang tanan, dili nato i-exhaust ang tanan nga computation, kato lang one statement nga if we do the computation of the union of X or the union of empty set to all other members of tau, the result are still open sets. So, mo nang na-satisfy ang condition. Kana. And kanina isa. Kani?
Kani, ma'am.
Kani
Last
siya.
topic, ma'am.
Kani sakto ni siya nga suggestion nga check the properties of a topology kay after getting the intersection of one topology to the other topology na at siya result nga set, no. So the next thing to do is to check the properties of a topology. Kani. Pero kani siya kay since this is the indiscrete topology, kung ako'y mag-justify ani ko ano lang siya. Kana. Note that T1 intersection T2 satisfies the three axioms to be considered as a topology. Thus T1 intersection tau2 is a topology. Pwede kayong ana ra kay kuan man gud ni siya ang indiscrete topology man ni. Pero kung dili siya indiscrete topology, then kadto undergo na to ang solution or computation sa reactions. So that's it. Thank you, Sir Paulo, and
Thank you,
congratulations.
ma'am. Thank you.
Okay, so we will now proceed ta sa kuan. Kinsay next presenter?
Ako, ma'am. Pwede mo na po, ma'am.
Sige, Sir Junel Butlig. Okay ra mo nga ang mo-volunteer lang na. Kaya na ko'y ganahan nga muuna na.
Ay, okay ra?
Sige, okay ra ko, sir.
Okay ra. Ako,
Sir.
sige, ma'am, para mahuman ako.
Sige, sir.
Okay, ma'am. Okay. Actually, ma'am, pwede mo gamitin na ako ang mobile phone, ma'am.
Pwede ra, sir.
Then, katong akong gisabit nga activity, ma'am, sa Google Classroom is na mga changes nga ang gipang-utro niya. Mo nang nag-send ko karon nimo kanang naay akong inutro, ma'am, sa Messenger. Kay dili naman ko ka-unsubmit sa Google Classroom.
Sige, sir.
Okay, ma'am.
Sa Messenger, akong access, sir, na-send na or wala pa?
Na-send na, ma'am. Na-send na.
Okay, sige. Sige, sir, pwede na
Kita
ka
ra, ma'am.
mag-start.
Ma'am, nang i-share
Pwede
screen,
na
ma'am.
ka mag-start og screen share.
Okay, ma'am.
Start na, sir.
Nakita na ba, ma'am?
Murag, wala pa man, tingali. Wala pa, wala. Kami pa ang nakita.
Okay. Kaya yung report, ma'am, nakita na, ma'am.
Kana, sir.
Parang ilan speak. So once again, good afternoon, everyone. So this is my report on our activity 1 in our topology. So for number 1, illustrate theorem 1.10, theorem 1.21, and theorem 1.23. So for theorem 1.10, I'm going to choose number 3. So here in number 3, so if A is a subset of B and B is a subset of C, then A is a subset of C. So let A be circle and square, and our B circle, square, triangle, and our C is a set circle, square, triangle, and hexagon. So if A is a subset of B and B is a subset of C, then A is a subset of C. So this states that if A is a subset of B and B is a subset of C, then A must also be a subset of C. So this follows the transitive property of subset relations. So in the set circle, square, subset circle, square, triangle, so this is the A subset B, then circle, square, triangle is a subset of circle, square, triangle, hexagon. Then the set circle and square is a subset of circle, square, triangle, and hexagon. So since A is a subset of B and B is a subset of C, so it follows that A is a subset of C. So next, illustrate theorem 1.21. So out of these 6, I will choose the commutative laws. So in the commutative laws, it states that A union B is equals to B union A, and for the intersection, A intersection of B is equals to B intersection of A. So let us have an example. So let A B equals to the set of apple and banana, and our B is the set banana and cherry. So for the union, A union B, so we have apple, banana, union of banana, cherry. So their union is the set apple, banana, cherry. So for B union A, so we have the set banana, cherry, union apple, banana. So their union is the set apple, banana, cherry. Thus, A union B is equals to B union A. Now let's proceed to the intersection. So A intersection of B is equals to B intersection of A. So our A here is the set apple, banana, intersection of banana, cherry is equals to banana, or the set banana. Then the intersection of our B intersection of A is banana, cherry, intersection of apple, banana is also banana. Thus, A intersection of B is equals to B intersection of A. So next, um, illustrate theorem 1.23. So in I will choose R2 number 3. So in the number 3, it states here that the complement of B is a subset of the complement A. So let's just say that let us have first suppose that our universal set here is 1, 2, 3, 4, 5, 6, and the subsets A is 1, 2, and B is the set 1, 2, 3, 4. So A is a subset of B because every element in set A is in set B. So for number 3, so the complement of B is a subset of complement of A. So let us say that the complement of B is 5, 6. So in our universal set, that is 1, 2, 3, 4, 5, 6. So augment or complement ang nasa set nga wala sa universal set. So ang complement sa B is 5, 6. Then the complement of A is 3, 4, 5, 6 since our set here is the set 1, 2. Thus, B complement is a subset of complement A. Kay naman nasod ang 5, 6 sa A. Then let's proceed to number 2. So provide example for the following concepts. So A, topology and topological space with detailed solution. Then B, open sets, closed sets, neighborhood of X for all element of X to X using the computed topology in 2A. Then letter C is larger topology. So A, topology and topological space. So by definition, a topological space is a set X together with a collection tau of subsets of X satisfying the following conditions. Number 1, the empty set and X itself are in tau. 2, any union of elements of tau is in tau. And 3, any finite intersections of elements of tau is in tau. The collection tau is called a topology on X. So let us have an example. Let's consider the set X be JOY or joy. Then our tau here is the empty set, the set J, set JO, and set JOY. Now let's verify that tau satisfies the conditions of a topology. So for number 1, does it contain the empty set and X? So of course, the empty set is an element of tau, and X, which is the set JOY, is also an element of tau. So number 2, we're going to check if it is closed under arbitrary unions. So consider any collections of sets in tau. So we have the set J union JO is equals to the set JO, which is an element of tau. The union of J and the set JOY is equals to JOY, which is also a set of tau. Then the union of JO and JOY is also JOY, an element of tau. Then the union of J and the set itself is J, which is an element of tau. So the union of all subsets in tau is empty set, union of set A, I mean union of set J, union of set JO, and union of set JOY is equals to the set JOY, which is an element of tau. So this is closed under arbitrary union. So check na siya. So next is if it is closed under finite intersections. So consider any finite collections of sets in tau. So J intersection of the set JO is equal to J, which is an element of tau. So J intersection of JOY is also the set J, which is an element of tau. Then the set JO intersection of JOY is equals to JO, which is an element of tau. Then J intersection with the set itself is also the set J, which is an element of tau. So the intersection of all subsets in tau is equals to empty set, intersection of J, intersection of JO, and intersection of the set JOY is an empty set, which is still an element of tau. Thus, tau equals to the set empty set, and the set J, the set JO, the set JOY is a topology on X. Now let's proceed to open sets, closed sets, neighborhood of X for all X element of X. So in that topology, tau defined above, the open sets are empty set, the set J, the set JO, and the set JOY. The closed sets are the complements of the open sets with respect to X. So the complement of the empty set is X, or the set JOY. Then the complement of J is the set OY. Then the complement of the set JO is the set Y, and the complement of the set JOY is empty set. So the closed sets are the set JOY, set OY, set Y, set J, and the empty set. So now let's proceed to the neighborhood of X for all X element of X. So a set N is a neighborhood of a point X, element of X, if there is an open set union, open set U such that X is an element of the universal universal set and a subset of N. So for X is equals to J, ang giyahang neighborhood is the set J, the set JO, and the set JOY. So for O, it is the set, these are the set JO and the set JOY. Then for y, it is the set JOY. Now, let's proceed to letter C, which is larger topology. So a larger topology on X means adding more open sets while still satisfying the conditions of a topology. So let us have an example. So let X be LBC and consider the two topologies. Tau sub 0 is equals to the set empty set X, the set L, the set B, and the set LB. Then for tau sub 1 is equals to the empty set X, set L, set B, set C, set LB, and the set BC and set LC. Then, tau sub 0 is a subset of tau sub 1. Now let's verify that tau sub 1 satisfy the conditions of a topology. So, does it contains the empty set and X? Yes. So, empty set is an element of tau sub 1 and X, which is the set LBC, is also an element of tau sub 1. So, that is checked. So, close under arbitrary unions. Excuse me. So, consider any collections of sets in tau sub 1. So, we have the set L union of set B is equals to the set LB, which is an element of tau sub 1. And set L union of set BC is equals to the set LBC, which is still an element of tau sub 1. Then set LB union set BC is equals to the set LBC is still an element of tau sub 1. So the union of all subsets in tau sub 1 is equals to LBC, which is an element of tau sub 1. Therefore, tau sub 1 is closed under arbitrary unions. Next, let's proceed to close under finite intersections. So consider any finite collections of sets in tau sub 1. So set L intersection of set B is equals to the empty set, which is still an element of tau sub 1. Then the set L intersection of set LB is equals to the set L, which is an element of tau sub 1. Then set B intersection of set BC is equal to the set B, which is an element of tau sub 1. So the intersection of all subsets in tau sub 1 is equals to, so ang ilang intersection is an empty set, which is still an element of tau sub 1. So since in each case, the intersection is either in tau sub 1 or is empty, which is also in tau sub 1. So tau sub 1 is closed under finite intersections. So since tau sub 1 satisfies all the conditions of being a topology on X, which is equal to the set LBC, we conclude that tau sub 1 is indeed a topology on X. So now let's proceed to number 3, excuse me, which is the theorem 3.11. So by definitions, again, topology is a collection of tau of subsets of X such that the empty set and X are in tau. The union of any collection of sets in tau is also in tau, and the intersection of any finite collection of sets in tau is also in tau. So let us have here an example. So let X be the set ABC, and our tau sub 1 is the set empty set X, the set A, and the set AB. And our tau sub 2 be the set empty set, the X, the set B, and the set BC. So the intersection of these topologies is tau sub 1 intersection of tau sub 2 is empty set and the X. So we're going to check the properties of a topology. So the empty set and X are in tau, which is indeed true. So any union of sets in tau sub 1 and tau sub 2, which are the empty set and X, is in tau sub 1 intersection of tau sub 2. So any intersection of sets in tau sub 1 intersection of tau sub 2 is also in tau sub 1 and intersection of tau sub 2. So therefore, the intersection of tau sub 1 and tau sub 2 is equals to the set empty set and X is a topology on X. So to illustrate that the union of topologies need not be a topology, so we're going to have an example. So let X be the set ABC. Then our tau sub 1 is the set empty set, the X, the set A, and the set AB. And tau sub 2 is the set empty set, the X, the set B, and the set BC. So the union of these topologies is the set empty set, the X, the set A, the set AB, the set B, and the set BC. So we're going to check the properties of a topology. So the empty set and X are in tau sub 1 union of tau sub 2, which is correct. Then A union BC is equals to ABC, which is not in the union of tau sub 1 and tau sub 2. So makita na ito nga walay set ABC sa ato ang union. Then for the sa last, so the set A intersection of BC is equals to empty set, which is in the union of tau sub 1 and tau sub 2. So thus, the union of two topologies on a set X does not necessarily yield a topology as evidenced by tau sub 1 union of tau sub 2, which lacks closure under arbitrary union. So that's all for my report. Hello? Thank you for listening.
Thank you, sir. Congratulations. Sige, ano ka sa comment? As far as reporting is concerned, no, how the examples are explained, okay kaayo man ang pa-explain. Well understood ni sir. Kuan lang, I've seen nga pareha mo og example ni sir kasi ni Sir Paulo sa first theorem 1.10 sir. And then sa last theorem po parehag example. Parehag example. Pero basin coincident lang sir.
Ay, kuan lang ma'am, kana nagpa-send man si Sir Paulo as kuan ma'am
Yes, ma'am.
reference.
Nagpasend ako reference niya, ma'am.
Okay, sige. Sige, ang comment nako sa asing comment lang man ako sa kuan sir. Katong how are we going to justify topology siya. Same comment earlier to. Ako lang siyang i-show ha. Kay kuan. Dali lang kayo. Kani sa number 2 example. Katong diri. Kanang how are we going to show that the arbitrary unions of any elements of the collection of tau. So ano to siya pag-show? Atong i-exhaust tanan ang kuan union sa tanang members of tau to all other members including the union of empty set and X. So kana lang siya ang i-answer. Puhon og napatay other exam para ma-complete ang justification why does the tau with respect to a certain non-empty set is closed under arbitrary unions, as well as sa intersection. Makita po na to ang pwede lang i-state na to nga the intersection of all other members of tau to empty is empty and empty is in tau. So okay na ta sa empty. Yan, the intersection of X to all other members of tau will be katong other members of tau no kay gamay man. Kung to siya ang gamay. So okay na po ta sa intersection of all other elements sa tau to X. So ang ato na lang i-final exhaust kay ang katong mga other elements. Kana ra siya generally. And then saan ito lang.
Okay ma'am.
Sige.
Thank
Thank you. Thank you, Sir Jimmy. Next, sa may next, we have Sir Lopera, Ma'am Aubrey, Ma'am Asuncion, and Ma'am Almami. Kisay mo una ninyo. Sir Lopera lang, Ma'am.
Kasi muna na to, man.
Sir Lopera.
Pwede rin ako, man, pero mahuman naman.
Kana na lang ang sequence, ma'am.
Sige. So we have Sir Lopera first and then Ma'am Ma'am Aubrey, niya, Ma'am Assumption, and then Ma'am Almamia. Sige. You have your hard copies man, no? Kaning 4.
Yes, ma'am.
Sige.
Yes,
Start na
ma'am.
ka, sir.
Am I audible to everyone?
Yes, sir.
Thank you, ma'am. Okay, good afternoon, everyone. Most especially to Dr. Josephine Binalsaro. Good afternoon, ma'am.
Afternoon, sir.
This this afternoon, I'm going to present my answers in our activity number 1 in this subject topology. But before I will start, may I ask if my presentation is visible and readable enough in your screens?
Okay na, sir. Nakita.
Yes,
Thank you.
sir.
Okay, so I'm so sorry with my penmanship kay medyo mao to gagi ang ballpen gyud. Mayo kay na ballpen pasanginlan. Okay, let me start presenting theorem 1.10. Let A, B, and C be any sets. So under theorem 1.10, we have three particular concepts. So since we are instructed to choose only one, so good thing for us that we're given the chance to choose. Kasi minsan sa buhay natin, makakaranas tayo ng walang pagpipilian. At ang mas masaklap pa dyan kung wala na nga tayong pagpipilian tapos di pa tayo ang pipiliin. Well, kidding
Oh, si
aside,
Sir Rafael, sir.
Charot, sir.
well, kidding aside, so I will choose number 3. So if A is a subset of B and B is a subset of C, then it follows A is a subset of C. So we need to prove this concept through giving an example. So we have here halimbawa, for example, in your screen, we have let A be equal to the set 0, 1, let B be equal to 0, 1, and 2, and let C be equal to 0, 1, 2, 3. As you can clearly see in your screen that A is clearly a subset of B because the elements 0, 1 are also in B. Every element of A is in B, and B is a subset of C, since 0, 1, and 2 are also elements of C. Thus, A is a subset of C since every element of A is also in C. So the elements 0, 1 are also present in set C. Therefore, we can say that A is a subset of C. Okay? So we have next, theorem 1.21. Sets satisfy the laws below. So we have various laws under theorem 1.21. So I will choose number 3, commutative laws. We have A union B is equal to B union A, and A intersection B equals B intersection A. So we have the commutative law for union, and we also have the commutative law for intersection. So the first one that I'm going to present is the example for the commutative law for union. We will let A be equal to the set 2, 4, and let B be equal to the set 4, 8. Then if we are going to take the union of the two sets A and B, it would be like the set 2, 4 union 4, 8 is clearly set 2, 4, 8, and B union A would be the set 4, 8 for B, and the set 2, 4 for A. It will give us the same result, which is the set 2, 4, 8. So since we have equal sets on both sides of our equation, thus we can confirm that A union B equals B union A is logically true. Now let's proceed to the example to prove the concept for the commutative law for intersection. Let A be equal to the set 1, 2, 3, and let B be equal to the set 2, 3, 4. Then, if we are going to take the intersection of the two sets given, we have A intersection B. The set A is given by the set 1, 2, 3. Intersection of the set 2, 3, 4. So we will have the result, the set 2 and 3. And for B intersection A, it would be set 2, 3, 4. Intersection set 1, 2, 3. And it will give us the result set 2, 3, which is equal to the first result that we have. Thus, we can say that since both sides of our equation are equal, so that means that A intersection B equals B intersection A is logically true. Now, for my overall conclusion or my final concluding statement with regards to the commutative laws under Theorem 1.21, the commutative laws demonstrate that the order of sets in a union or intersection does not affect the result. So it means if even if we are going to change the positioning or the order of the sets um, in a union or intersection, as long as we are considering the same sets, it will not affect the result. Okay, now let's move on. Kahit alam naman natin na minsan mahirap ang mag-move on. Ingon bitaw sila nga, para dili na mo taas ang imong kasakit, dapat move on. Well, joking aside, let's now have Theorem 1.23. Each of the following conditions is equivalent to A subset of B. So I will choose number one, whether you like it or yes. I will choose number one. A intersection B equals A. So I choose number one because I think this is somehow synonymous to priority, yung lagi kang inuuna. So number one ka sa buhay niya. Okay, so let's have halimbawa, for example, for the concept number one. So if A is a subset of B, then A intersection B equals to A. So we have let U equals the set 0, 1, 2, 3, 4. And for set A, we have 3, 4. Set B, we have 3, 4, 5. So clearly, as you can see in the given sets above, A is a proper subset of B. So when we speak about proper subset, it means that it is still a subset, but it is still a subset that contains some of the elements of the original set, but not all. So we have, let's continue. So A is a subset of proper subset of B since every element in A is also in B. So we have the elements 3, 4 are elements also of the set B. Now, let's take the intersection of the two sets. A intersection B, let's focus on the sets A and B. So the intersection of A and B is obviously the set 3, 4, which equals to the set A. Thus, we can say that A intersection B equals to A is true, confirming that A is a subset of B. Okay, so next, let's have number two, topology and topological space. So again, we are instructed to give examples for or illustrations for number two. So example of topology, let A be equal to the set 2, 4, 6, 8, 10. And we have this collection of subsets. Since we cannot say as of this time that this is a topology because we need first to verify or to check if it follows the three necessary conditions or actions. So we have the collection of subsets. We have empty set. We have A, the set 2, set 2, 4, set 2, 4, 10, set 2, 4, 6, 10. Okay, so let us have first axiom 1 or the condition number 1. Each union of members of tau must be also a member of tau. So I have here the detailed solution. So for the first, let's say the first column, the union of any non-empty set with an empty set is always equal to the non-empty set itself. So we have empty set union A, we have A. Empty set union set 2, we have 2. Empty set union 2, 4, 2, 4. Empty set union 2, 4, 10, 2, 4, 10. Empty set union 2, 4, 6, 10, we have 2, 4, 6, 10. So for the next member of tau, we have A union set 2, we have A union 2, 4, we have A union 2, 4, 10, we have A union 2, 4, 6, 10, we have A. And A is a member of tau. Now let's proceed to set 2 union 2, 4. We have 2, 4, set 2 union 2, 4, 10. We have 2, 4, 10. Set 2 union 2, 4, 6, 10. We have 2, 4, 6, 10. 2, 4, 2, 4, 10, 2, 4, 6, 10 are all members of tau. So we have 2, 4 and 2, 4, 10 union. We have 2, 4, 10. 2, 4 and 2, 4, 6, 10. We have 2, 4, 6, 10, which are all members also of tau. So the condition number 1 is already verified. Let's proceed with condition number 2 or action 2. Each finite intersection of the members of tau is also a member of tau. Now, let's have the intersection of an empty set with a non-empty set. So the intersection of an empty set with a non-empty set is always equal to an empty set. So we have here, empty set is a member of tau. So next we have the union of I mean intersection of A and set 2. We have 2, A intersection 2, 4, we have set 2, 4. A intersection 2, 4, 10, we have 2, 4, and 10. A intersection 2, 4, 6, 10, we have 2, 4, 6, 10. So next we have set 2 intersection 2, 4, we have 2. Set 2 intersection 2, 4, 10. Set 2. Set 2 intersection 2, 4, 6, 10, we have still set 2. And set 2 is a member of tau. Set 2, 4 intersection of 2, 4, 10, we have set 2, 4. Set 2, 4 intersection of 2, 4, 6, 10, we have set 2, 4, which is also a member of tau, as you can see above. Okay, so the last condition, the last axiom, we have empty set and X are members of tau. Since in my example, I did not use X kasi hindi ako mahilig manggamit ng X. Siya lang ang nagamit sa akin. Joke lang. Okay, so we have empty set and A. So since it satisfies all the three important conditions, since the collection of subsets satisfies all the necessary conditions, before we can say that this collection represents a topology. So kay na-satisfy man niya, so it means the given collection of subsets above represents a topology on A. Now let's proceed with example of topological space. Topological space, a couple X and tau. So since I'm using A to represent my original set, so we have here A and tau consisting of a set of A and a topology tau in A given above. So we have here the topological space. So I just combined the original set A and also the proven topology. So we have here 2, 4, 6, 8, 10, and the topology proven above. We have empty set A, set 2, set 2, 4, set 2, 4, 10, set 2, 4, 6, 10. Okay, so now let's proceed with the tau open sets and the tau closed sets. Consider first A, which is equal to 2, 4, 6, 8, 10, and topology denoted by tau. We have empty set A, set 2, 2, 4, set 2, 4, set 2, 4, 10, set 2, 4, 6, 10. Now let's have first the tau open sets. The tau open sets are just the members of our topology above. So each member of tau is always considered as an open set. So all members of tau are the open set. So we have here empty set A, set 2, set 2, 4, set 2, 4, 10, and set 2, 4, 6, 10. Now for the tau closed sets are as defined. Um, these are just the complements of our open sets. Since I am not using x, so sa ato ang notes ani x minus o man eh. But here I'm using a, so this is a minus o. So we have to subtract a from empty set. So we will have a minus a, we have empty set. A minus set 2, we will have the set 4, 6, 8, 10. A minus set 2, 4, we will have 6, 8, 10. A minus 2, 4, 10, we will have 6 and 8 as the complement. And also, the last one, A minus 2, 4, 6, 10, we have 8. So, those are the tau open sets and the tau closed sets. Now, let's proceed sa neighborhood of x for all x in A. I mean, for all x in X. Since I'm using A, so nainga niya akong statement, neighborhood of A for all A element in A, which are the following. So the neighborhoods of 2, so when we recall the definition of neighborhood, that is any open set that is a member of tau containing X. So in this case, I'm using A, so containing A. So the neighborhoods of 2 are A, set 2, set 2, 4, set 2, 4, 10, and set 2, 4, 6, 10. And for the neighborhoods of 4, we have A, set 2, 4, set 2, 4, 10, and set 2, 4, 6, 10. Now for the neighborhoods of 6, we have A and 2, 4, 6, 10. The neighborhoods of 10, we have A, 2, 4, 10, and 2, 4, 6, 10. So if you're wondering why we don't have the element 8 in our neighborhoods, it's because wala may silingan si 8 diri. Ganahan siya maginusara siguro. Okay, so wala siya in neighborhood dire. Naka-experience na ba mo maginusara? Ako, naisip ko minsan na gusto kong mapag-isa kaso di ko na lang tinuloy kasi wala akong kasama. Well, joking aside, let's proceed. We have for our larger topology. So we will let A be equal to 2, 4, 6, 8, 10. And for our tau sub O, so kini si tau sub O mao ni ang ato ang proven topology sa number 2A. So we have empty set, A, set 2, set 2, 4, set 2, 4, 10, set 2, 4, 6, 10. So naa na tayo detailed solution ani. So I will no longer provide the detailed solution for tau sub O, but for tau sub 1, we have here the detailed solution below. But we have to prove first if this collection of subsets satisfies the three important conditions before we can say that this collection represents a topology. Okay, so we have for axiom 1, the union of members of tau must also be a member of tau. Since medyo lengthy ang solution, uh, I will not do it one by one, but instead, I will just focus on the results kung member ba siya sa ato ang tau sub 1. So we have A, 2, 4, sa 2, 4, 2, 4, 6, 2, 4, 10, 2, 4, 6, 10 na siya sa ato ang tau sub 1. Then the second column, let's say the
Bless you,
second
sir.
column, for the second column, we have A, is a member of tau sub 1, 2, 4, 2, 4, 2, 4, 6, 2, 4, 10, 2, 4, 6, 10. Members also of tau sub 1, 2, 4, 2, 4, 6, 2, 4, 10, 2, 4, 6, 10. Members of tau sub 1, 2, 4, 6, 2, 4, 10, 2, 4, 6, 10. Members of tau sub 1. Sorry. And we have 2, 4, 6, 10, 2, 4, 6, 10. Members of tau sub 1 also. And we have 2, 4, 6, 10. Member of tau sub 1. So we are done verifying axiom 1 or condition number 1. Let's proceed with the finite intersection of members of tau, um, and it should be also a member of tau. The intersection of a non-empty set with an empty set is always equal to an empty set. So we have here, and we have 2, 4, 2, 4, 2, 4, 6, 2, 4, 10, 2, 4, 6, 10 members of tau. Empty set 2, set 2, members of tau. Then we have set 4. The results are set 4, which is also a member of tau, tau sub 1. 2, 4, 2, 4, set 2, 4, set 2, 4, 6, and set 2, 4, 10, which are also members of tau sub 1. Now, for the last condition, we have empty set and X are members of tau. So again, since I'm using A to represent my original set, so we will have empty set and A, which are present in our tau sub 1. So therefore, we can say that this collection of subsets represents a topology. And now, since as you can see that in tau sub 1, we have more open sets or finer sets compared to tau sub O. So meaning to say that tau sub O is just a subset of tau sub 1, and therefore tau sub 1 is finer than tau sub O. And okay, so this is continuation is akuan. So, I'm sorry for this kay nagdubli. So kung atong i-relate ni sa ato ang subject kay more on proving man ta, this proves nga sayop gyud ay magdubli. Magdubli-dubli. Sama ani. Okay? O daghan na kay dubli. Okay. Ma'am sa ako ang napas nga hard copy. So wala na humahuman tong awang 3.11. Pero naapod na ako dire ang hard copy para sa 3.11.
Sige sir,
So ako
submit lang na siya on Saturday puhon.
okay ma'am, thank you ma'am. Okay, so the last but definitely not the least, theorem 3.11. So let X be equal to the set A, B, C. So sa mga previous examples no, I did not use X as example. Wala ko mag-denote ni X, di ba? Okay, because I think nga nanong bakit naman ako maghahalimbawa ni X kung di naman siya magandang halimbawa? Well, daghan kasi na nagtawa. Okay, so this time nagamit na ko ni X to denote my set, but don't worry kay gipawahi man nato sa X kay dili man siya priority. Well, let X be equal to the set ABC. Now, let's define two different topologies on X. So, by assumption, assume na lang nato nga kini dili na nato i-prove ni pero kini gyud silang duha kining tau sub 1 and tau sub 2 are two different topologies derived from this original set X. Now, we have tau sub 1 set empty set A, set BC, and set X. Tau sub 2 empty set B, set BC, and X. Now let's take the union of tau sub 1 and tau sub 2. So the union of tau sub 1 and tau sub 2 is equal to empty set. So we will take the union. Empty set A, set B, set BC, and set X. Now let us try to verify. So we're going to verify if the union of two topologies will result to a topology or not a topology. So first, we have empty set is an element of tau sub 1 union tau sub 2. So we have here empty set, and X is an element of tau sub 1 union tau sub 2. So we are then verifying the first condition. So next is the intersection of tau sub 1 and tau sub 2 is, so we will get the intersection. Take the intersection of tau sub 1 and tau sub 2. So we will have empty set B, set BC, and X, which is a topology on X. So now, let's have the third condition. So tau sub 1 union tau sub 2 is closed under arbitrary unions. Consider, so the elements or the sets A and set B are elements of the union of tau sub 1 and tau sub 2. We have set A and set B. But if we are going to take the union of set A and set B, it will give us the result set AB, which is not an element of our tau sub 1 union tau sub 2. So you cannot find set AB here in our union. So therefore, it um, it fails to follow um, the condition that the union of the members of tau must also be a member of tau. So therefore, we can say that tau sub 1 union tau sub 2 is not a topology in X since it fails to follow one of the three necessary conditions. So we can further conclude that theorem 3.11 demonstrates the union of two topologies may or may not be a topology. So meaning to say, it does not necessarily mean nga og mag-combine tag two topologies mo result po siya og topology. It could be, the result could be a topology or not a topology. And that ends my presentation. Thank you so much, everyone, for listening. I hope that you have learned something from my presentation, and I hope that you enjoy listening to my jokes and hugots. And before I finally end my presentation, allow me to leave this hugot to all of you. Sabi nila, ang totoong nagmamahal ay parang isang mabuting estudyanteng nag-i-exam. Hindi tumitingin sa iba kahit nahihirapan na. Once again, dagang salamat. And that's all.
Thank you,
Thank you,
sir.
ma'am.
Thank you, Sir Lopera. Wala
Yes,
ko
ma'am.
ka-move on sa mga hugot, sir, no? Sige. So, para mapatawad mo na si X, sir. I'm gonna give you some good points when you do your presentation. So, as to sequence of arguments, sir, it's good, sir, know that you have clearly stated from the start of the statement, and then the next statement, the argument for the next statement, as well as the conclusion is clear. So, mayo to siya. It's that's the way how are we going to prove pure mga theorems or kanang justify results or even examples. So, pwede na ka mag-write of articles. And as far as computation of solutions is concerned, accurate ang proof, ay accurate ang computation and complete. Kuan lang, aside from being a good hugotero, katurong one comment na ko, sir, sa example number 2 on open sets on the neighborhoods of 8. Muragi, exclude ni mo si 8, sir. Parang
Oh,
may
yes.
may
Award
hatred
mo.
ka ni 8. Katong sa
Favorite
8,
number ba yan naman kay birthday na una.
amo di ay. Katong sa 8, sir,
Wala na huma.
dapat na adyo neighborhood, no?
Naagi siya neighborhood mo, pero wala lang sa atong example.
Na kuan, if wala siya sa
Basta
mga smaller set, the only neighborhood of 8 is the
is
set X or the set A sa imong case.
okay.
Ano, so sa tanan nga mga points A in A, all the rest have more than one neighborhood. So
Yes,
daghang
ma'am.
sets nga ni continue. For 8, basta lang iyang neighborhood. It's only X because or A because it's the larger set. So kung wala man gani mga smaller set, it's A. Katulad
It's
ko
A, ma'am. Dit dit dito
99
dito dito ko nagkuwang, ma'am.
doon ka nagkulang, sir. Wait lang. Katula. So the rest, okay ang computation. Kalimot na noon ko, sir, kay na-overwhelm ko sa mga hugot.
Siyaw lang, ma'am, para di nakatugon, ma'am.
Wait lang. Any comments, sir? Rafael, Kaitong.
Nasakitan daw sila
Tawag.
ma'am.
Nasakitan.
No, nasakitan ko gamay, Ma'am Banjo.
Ah, sige, kuan di ay pud sir
Naigo
no.
ka, Sir Raf.
Kuan day sir. I tried to check Dogon G and Shoms. Sa kong gi-check kay katong you are making use of another variable no instead of x.
Yes, ma'am.
Murag
Nag-A ko, ma'am.
convention niya pero okay naman wala may problem. Ang mga convention nga gigamit sa Dogon G o sa Shoms kay x yun ilang gamiton for an
Ah,
empty set nga dili siya known like R katong the set of rational numbers kanang mga known nga set like the set of integers ang ilang gamiton kay z gyud the set of natural numbers
mm,
known naman nato siya but if it's an
yes.
arbitrary
Yung noon
non-empty
yung mga
set,
denotations, ma'am.
yes sir if it's an arbitrary empty set x ang gamiton but so far wala ray
Okay, ma'am.
problema man sa computation kung ano
Tama
lang
ba?
just sharing sa mga
Okay, ma'am.
notations nga gigamit
Yung X
sa
nga sunod gamitin ako, ma'am.
oh para mapatawad mo na
Parang
si X.
wrong about ka. Joke lang.
Para maka-move on na. Ikaw, kato sir, mo to good kaayo ang sequence sa computation and accurate solutions. Okay, some other comments. Maayo man day ka ipakuan na to sir no kay
Thank,
kita
thank you,
ka
ma'am. Ginahuman na ko.
kung natay program ikaw among ipa-MC kay para dili ka tuloy. Sige, so okay na ta. Let's proceed to the next reporter. Ma'am Muso, Aubrey, si Ma'am Aubrey to no? And then
Yes, ma'am.
Ma'am Pania and Ma'am Putong after.
Okay, good afternoon, ma'am. Madungog ra ko.
Yes, ma'am.
Okay, so I don't have my hard copy, but I have my soft copy, and I prepared a PowerPoint presentation to aid me kay di ko kitag klaro mo katong sa ako ang gi-send of soft copy. I have visual disability. So makita na ang akong screen, ma'am. Hello.
Wala, ma'am.
Presenting pa, ma'am.
Medyo hinay ako ang makita na akong screen, ma'am.
Not yet, ma'am.
That's it. I got loading. Wag yapon, ma'am.
Wala
Hello?
gihapon, ma'am.
Imong now mo nakita, ma'am, together with
Ha?
your hubby.
Kuan tingali, ma'am. Stop screen share niya. Share balik. Wala gyapon nakita, ma'am.
Na ma'am, wa gyud.
Wala gyapon.
Imo rang profile pic, ma'am.
I-open daan guro ng imuhang kuan ma'am, imuhang PowerPoint. Amo to imong ano.
Na na open ko na. Kay
Unya. Then i-click tong PowerPoint nimo ma'am.
Inana po nakuha, ma'am, di ma-open.
Basin hinay ang internet connection sa inyo ha, Ma'am Aubrey.
kaya ma-switch na lang ko sa kuan ma'am sa tablet.
Sige, ma'am. So, mag-wait me, ma'am, or
I-proceed na si ma'am kuan, Asuncion.
sige. And then ikaw after.
Oh, sige ma'am, sige.
Sige. So, can we have Ma'am Asuncion and then Ma'am Aubrey and then Ma'am Alma?
Yes, ma'am. Makita ra, ma'am?
Yes, ma'am. Makita na.
Okay, ma'am. So, it's so good afternoon, everyone, especially to Dr. Josephine Alzaro. So, I am going to present the activity 1. Now, kaya ka, Sir Lupera, no? Sorry, kaya akong penmanship is not that good. I-blame na to sa ballpen. Okay, so for theorem 1.10, I'll choose the first one, which is A is a subset of A. So wala na ko nag-show example ani ma'am, ako na lang di-state nga let X be an arbitrary element of A, then X is in A. Since X was arbitrary, this shows that all elements in set A will be also in another set A. So it means that A is a subset of A. Or shown here, A is a subset of A where X is kanang element of A for all X element in A. So for theorem 1.21,
Ma'am Aubrey.
so for theorem 1.21, I'll choose idempotent clause. So we have here A union A will be equal to A and A intersection A will be equal to A. So let A, the set of 1, 2, 3. Ma'am, I don't know lang ma'am ha, pero kanin siya ma'am, wala dyan may ka nang nagkopyaan ma'am, no, maybe ang number ang 1, 2, 3 or 1, 2, 3, 4 is most convenient sa amuang tanan. So we have here let A be the set, the element of 1, 2, 3. So A union A is 1, 2, 3. I mean the elements 1, 2, 3 union the another elements of 1, 2, 3. And we shown here that the A union A is equals to A. Now, for the second one, let A, the element again, 1, 2, 3, then A intersection A, 1, 2, 3, intersection 1, 2, 3. So A intersection A will be equal to the A, set A. So let's proceed to, excuse me, 1.23. So I'll choose letter A. A intersection B will be equal to A. So let A be the element of 1 and 2, and let B with the elements of 1, 2, 3, and 4. So we have here A intersection B, we have A, 1, 2 intersection with the elements of B, 1, 2, 3, 4. So the intersection of both sets is 1, 2. So therefore, we shown here that A intersection B is equals to A. Next one. Topology. Okay, so next one is provide example for a topology, topological space, the open sets, closed sets, neighborhood of all X and the larger topology. So we have here A, an example of topology and topological space. So let X be 3, 4, and 5, and the tau would be empty, singleton 3, the elements 3, 4, and X. So to show that the tau is a topology on X, we need to it should be satisfying the three conditions. So first is each union of members of tau is a member of tau. Then second, each finite intersection of the members of tau is also a member of tau. And lastly, null set and X are members of tau. So here are the solution. So we have here first condition, union of tau. So we have the tau null set, singleton 3, 3, 4, and X. So we have here first, we get the union of the null set with the tau. Next, we have the union of singleton 3 with all the taus. We have the elements 3 and 4, union to all the tau. And lastly, we have the X union to the tau. So in this solution, hence condition 1 is satisfied. Now let's proceed to the second condition, the intersection of tau. So we have here the X again, the elements 3, 4, 5, and the tau. So in this solution, I showed or presented the intersection of null set to the tau, the intersection of the singleton 3 to the tau, the intersection of elements 3 and 4 to all taus, and X intersection to all tau. Then in this solution, hence condition 2 is satisfied. Now for condition 3, null set and X are members of tau, while the empty set is an element of tau and X is an element of tau is true. Therefore, tau is a topology in X. Now next one, we have here the open set, closed, and neighborhood. So for the open sets, the tau open sets are null set, the singleton 3, elements 3, 4, and X. Now for the closed sets, we have the T closed sets. We have the empty, the elements 4 and 5, the singleton 5, and the X. Now next one, the neighborhood. Neighborhood for X, for all X in element of X. We have for 3, we have 3, 3, 4, the elements 3, 4, and X. For number 4, the X equals to 4, we have their neighborhood, the elements 3 and 4, and X. Now for 5, we have the elements of, all X. Now let's proceed to the larger topology. So I just added the tau sub 1, which is the null set, singletons 4 and 5. We have elements 3, 5, and elements 4, 5, then the X. So tau sub 0 is already verified, shown here in number 2A. Then we'll show, or in this solution, we'll show if tau sub 1 is also a tau, or tau in T, or topology rather. So we have here, so the union of tau sub 1. So as shown here, all the unions of null set to the tau, the singleton 5, singleton 4, union of singleton 4 to the tau, the elements 3, 5, union of elements 3 and 5 to the tau, union of 4, elements of 4 and 5 to the tau, then X. So as shown in the solution, the condition number 1 is satisfied. So let's proceed to the second condition if tau sub 1 is tau in topologies in X. So we have your intersection of null set to the tau and so on. So the other taus, intersection of them to the tau. So by this solution, we can conclude that condition 2 is satisfied. Now also for the last condition, it is also satisfied because null set is an element in tau and X is an element in tau. So we have here theorem 3.1. So we have here, let x be 1, 2, 3, 4. Then tau sub 1, we have the null set x 1, 1, 2, 1, 2, 3. And tau sub 1, null set x singleton 2, elements 3 and 4, 2, 3, 4, B topologies in X. So we have here the union of tau sub 0 and tau sub 1. So the null set and X is confirm a topology. Now for tau sub 0, tau sub 0 intersection tau sub 1 is a topology, and tau sub 0 union tau sub 1, we have here null set X singleton 1, 2, elements 1, 2, 3, 4, 1, 2, 3, and 2, 3, 4. So when one or singleton 1 union the elements of 3 and 4 will be equal to the elements of 1, 3, and 4 for all elements in tau sub 0 union tau sub 1. So in this illustration, we can say that the intersection is always a topology, but not necessarily a topology for union A or kaning subscript A, tau, then another tau topology. So that's the end of my reporting.
Let's give a virtual applause to Ma'am Pania. Thank you, Ma'am, for the presentation. Okay, asam to imong hugot, Ma'am.
Sure, different.
Sala yun din ni Sir Lopera, Ma'am.
Pero manggod mo.
Kung hatag siya hugot. Bitaw, sige. Comments, as far as computation is concerned, complete no present ang computation. Lang, for the term illustrate, sa ako ma'am, I mean the example. So okay man ang proof, but kung illustration, I am looking for the example instead of the proof. Then kato lang ma'am, katong sa topology bitaw, when we are to show for a collection tau to be a topology, katong first ni mga solution ma'am ay union of tau. Pwede lang at adan lang to na to ma'am, union of elements of tau. Kaya ang atong union are the elements.
Sige na.
Dili gyud sa tau niya. Atong intersection po na to, intersection of elements of tau. And katong mga x bitaw ma'am.
Yes, ma'am.
Katong gipang hate na to nga mga x. Kuan. Dili na to siya enclose in a brace ma'am. Kung dili na to enumerate ang
Okay. X na dayon, ma'am.
okay. Mo naman to ang representation sa set. So if we will not make use of the x, kato atong gamiton si whole elements of the set. So kato si 3, 4, 5 atong gamiton. That's the time that we will use the brace. And overall, minor wala ra error ang computation. So,
Thank you, ma'am.
thank you and congratulations. Next, shall we proceed to kuan? Okay na ba ka, Ma'am Aubrey? Ready na ka?
Yes, ma'am. Sige.
Sige ba, doon.
Okay na, ma'am. Makita na.
Yes, ma'am. Kita na. So, pwede na ka, ma'am.
Thank you. Nag-cooperate yun siya. Okay, so, okay na, ma'am. Na.
Yes,
Hello.
ma'am. Start
Sige.
na, ma'am.
Okay, so good afternoon. Today I will be presenting my assignment in topology. Okay, so we have number 1, illustrate the theorem 1.10, theorem 1.21, theorem 1.23. So theorem 1.10. I choose number 2. If A is a subset of B and B is a subset of A, then A is equal to B. So let A is equal to M and O, and B is equal to O and M. So A is a subset of B. This implies that all elements of A are elements of B. And B is a subset of A. This implies that all elements of B are elements of A. So this implies that A and B consist of the same elements. Therefore, A and B are equal. Okay, so I will proceed with Theorem 1.21. I choose associative laws. So associative laws, A union of B union of C is equal to A union of B union of C. And A intersection of B times intersection of C is equal to A intersection of B intersection of C. So let A is equal to A and T, and B is equal to TAP, and C is equal to SAP. Then a union of A and B union of C is equal to P A and T union SAP is equal to P A N T and S. So, and A union of B union of C is equal to A and T union T A P S is equal to P A and T S. Thus, A union of B union of C is equal to A union of B union of C. And A intersection of B times intersection of C is equal to AT union of SAP is equal to A, and A union of B union of C is equal to A and T union of AP is equal to A. Thus, it's not intersection rather. Thus, intersection of B intersection of C is equal to A intersection of B intersection of C. Kanang okay ra pacing ko, ma'am?
Okay lang ma'am, pero kanang wala ka nakasubmit na kog hard copy ma'am, no?
Wa, ma'am, kan soft copy lang.
Sakto ba? Sige. Sige na ma'am, go on. Follow ako sa imong discussion.
And then we have theorem 1.23. I choose number 1. A union of B is equal to A. So let A is equal to 1, 2, 3, and B is equal to 1, 2, 3, 4, 5. Then A intersection of B is equal to 1, 2, 3. Intersection of 1, 2, 3 for A is equal to, kalimot pagbutang, is equal to 1, 2, 3, which is equal to A. Therefore, A is an intersection of B is equal to A. So number 2, provide example for the following concepts. A, topology and topological space with detailed solution. So let X is equal to M N O P Q and tau is equal to MT X M O P M O P N O P Q. A collection of tau of subsets of a non-empty set X is a topology on X if it satisfies the following axioms. So we have axiom 1. Each union member of tau is a member of tau. So MT union of X is equal to X is a member of tau. X union of M is equal to X, that is also a member of tau. M union M and O is equal to M and O, member of tau. N O union of NOPQ is equal to NOPQ, also a member of tau. And M and O union with NOPQ is equal to X, also a member of tau. Then we have the number 2, each finite intersection of the member of T is of tau is a member of tau. So MT intersect with X is equal to tau, that is MT, that is a member of tau. X intersects with M is equal to M, member of tau. OP intersects with MOP is equal to OP, member of tau. MOP intersects with NOPQ is equal to OP, also a member of tau. And number 3 axioms, third axioms, MT and X are member of tau. Tau satisfies the necessary 3 axioms given above, thus tau is a topology on X. So we have letter B, open sets, closed sets, and neighborhood. So let X, I use the same topology. X is equal sets of topology, and we have let X is equal to MNOPQ, and tau is equal to MTX MOP MO MOP MOP NOPQ. So open sets. An element of O or of tau is called a tau open set. Then tau open sets are MTX MOP MOP and OPQ. Closed sets, the complement X over O is called a T-closed set. The T-closed sets are X, MT, and OPQ, M, and Q, and Q and M. For the neighborhood of an X, element of X is any open set that is a member of tau containing X. So I use M. Let M be an element of X, then the neighborhoods of M are X. The neighborhoods of M are X, M, and MOP. So, isa lang akong gigamit ng example for the neighborhood. Then, we have the larger topology. Let X is equal to M and O and consider the two topologies. Tau 0 is equal to MTXM, MN, and tau sub 1 is equal to MTX, MO, MN, and MO. Then, tau sub 0 is a subset of tau sub 1, thus tau sub 1 is finer than tau sub 2. For number 3, illustrate theorem 3.11. Let X is equal to M and O and consider the two topologies. We have tau sub 1 is equal to MT, X, M, N, MN, and tau sub 2 is equal to MT, X, M, O, MN, MO. Observe that tau sub 1 intersects with tau sub 2 is equal to MTX, MN is also a topology in X. However, tau sub 1 union with tau sub 2 is equal to MT, X, M, N, O, MN, and MO is not a topology. It's not a topology in X since MO is an element of T1 union to tau sub 1 union with tau sub 2, but N union with O is equal to NO, and it's not an element of tau sub 1 union with tau sub 2. So that's all. Thank you very much. Bye, Kuya Hugot.
Thank you, ma'am. Congratulations, Ma'am Lobbery. Sige, Anita, start sa... Anindot ka voice, ma'am. Pwede pang call center. Anita, start sa theorem 3.11, ma'am. Wala pa siya wala pa nimo siya gi-stop. Screen share.
Ay.
Si your okay ra katong last, ma'am, na
Ano?
theorem. I cannot access your soft copy kay daghan siya kaayo mga pages no ni wala na ko siya na download, wala siya na usa ka PDF. So there is a
Makita na.
theorem. Makita ra, ma'am, ana ra, ma'am, hayo sa stop. However, T sub 1 union T sub 2. Our T sub 1 is MTX, MNO, MN of MO. So union of MN and MO, MNO, no? X. And then NO. Dili siya topology since MO is in tau sub 1. Tinuod siya. Kanilang typo error ka ni, ma'am, no?
As
M